Hello, my name is Simon Tarbush, and today I'm going with Punjan Zhang to present our work entitled Mutual Coupling Aware Channel Estimation and Beamforming for RIS-Assisted Communication. This paper has been accepted for publication in IEEE Transaction on Wireless Communication, and it's a joint collaboration with Dr. Hadi Sareddin from AUB and Prof. Tariq Al-Nafouri with King Abdullah University of Science and Technology. Okay, let me first start by defining the system model we are considering. We have a user that attempts to communicate with a base station through an active race. We assume in this model that the channel between the user equipment and the base station is blocked. Each of these entity has a uniform planar array with proper sizing. For example, for the user equipment, we denote it by NU. And our assumption are the propagation in the far field settings, and we assume a narrowband system at high frequency, for example, millimeter wave, sub-terahertz, so on. Okay. Our goal is to estimate the channel while considering the mutual coupling. So the mutual coupling aware, which we will denote through this presentation HMC, and this is the cascaded channel considering the mutual coupling, is equal to HIU, which is the channel between the user equipment to the RIS, multiplied by the effective RIS response, which accounts for the mutual coupling, multiplied by HBI, which is the channel between the RIS and the base station. Okay, this term, the effective RIS response, is composed mainly of two matrices and is derived based on microwave network theory from this reference. Okay, what is this? For any microwave circuit with N port, here in our case it's an I port, we can characterize the elements of this network through the scattering matrix, which is basically we can derive from one port with an incident wave voltage from the jth port, and by assuming all other, there is no incident wave from all other ports by using a matched load, and then we measure out the reflected voltage signal or wave coming out from the ith port. Okay, so this is by using this matrix, we can describe actually the mutual coupling for this RIS. And the second term is the RIS response matrix for the ith element, gamma I, for example, is equal to the amplitude factor multiplied by the phase response. Here is amplitude factor, since we have an active RIS, belongs to R plus, and of course we will add later some power constraint on the total power, and multiplied by a phase shift, which is we assume belongs to the interval 0 to 2 pi. Okay, so this model, once we assume S is 0, reduced to the conventional model. Then in our work, we are basically considering the effect of mutual coupling in such wireless scenario. Okay, basically we have the conventional channel model. We know it's the cascade channel is a multiplication by the RIS response, which is in this case is diagonal. However, once we adopted the mutual coupling, we can see that this is the diagonal structure. However, the S is a full matrix, then the effective RIS response is no longer diagonal. Hence, many questions arise. First, we know at high frequency, basically we can use compressed sensing techniques to estimate the channel. So first question, can we use compressed sensing technique to estimate the cascaded channel for this model? The second one, what are the effects of the mutual coupling on channel estimation? And the third question is mutual coupling a performance limiting impairment for the beamforming stage, or we can do for example, some optimization for the RIS and benefit from such an effect. Okay, so this is what we are going to see in this presentation. But before going into these details, Let me present a background on compressed sensing and some mathematical tricks that we typically use, and then introduce the basic model, which is a communication system. We want to estimate the channel between the user and the base station, and then we can add the RIS and see how the formulation it is. Okay, I will start by presenting some important mathematical tricks. The first one, we have three matrices, of course, with proper dimension for making this multiplication valid. The vectorization of ABC is equal to the canonical product of the transpose of matrix C by, as we mentioned, canonical product by matrix A multiplied by vec B. The second trick is, let us assume M a matrix with dimension n1 by L, M2 is with dimension n2 by L, and here is the important thing, let us assume gamma is a diagonal matrix, then this multiplication from canonical product multiplied by vec sigma is equal to the column-wise Hartree-Rho product multiplied by the vector containing the diagonal elements. Why this is important? As we can see, the dimension for such a product is n1, n2 multiplied by L squared. However, for the column-wise Hartree-Rho product, this dimension is n1, n2 multiplied only by L. Okay, and also within this presentation, we will use notation for this notation for row-wise Hartree-Rho product. Okay. Let us now start with the basic formulation for a user equipment that is trying to communicate with the base station on the uplink, and we are trying to estimate this channel using the compressed sensing technique. Okay, so what is the channel? We will denote it HPU is a summation over multipath for a complex gain multiplied by the steering vector from the base station multiplied by the steering vector from the user equipment. So after arranging this summation in a matrix form, we can write the channel as multiplication of two matrices multiplied by what we called the beam space domain. Okay, so what is our target? As we mentioned, our target is to determine the channel parameters. Basically, given this geometric channel model, what we need to estimate is the vector of complex gain and the vectors of angle of arrival, angle of departure, and angle of arrival. Here, every component is a vector since we have azimuth and elevation angles. Okay, so what we typically do in compressed sensing settings, we do some trainings. We can understand that the training weights for the precoder or the combiner is a beam directed to certain direction, and we are picking up some random vector and do the training. Okay, let me start with the first step, the user equipment. Use a training precoding, we will denote FMU, and the base station employ a training combining vector WMB. Okay, this is, we collect the received signal for a measurement, for the first measurement, which is denoted YMUMB. And with proper definition of the noise, the received signal for this first measurement, MUMB, appeared because it's the channel multiplied by the precoding vector multiplied by the Hermitian of the training combining vector. Again, we can now apply the first trick presented in the previous slides, and we will get this form. However, this is for one measurement. Now, typically what we do, like the user equipment for this, the first measurement, the base station for this measurement, apply MB distinct random combining vectors. And then the user equipment send another beam, and the base station apply other MB distinct random combining vector, and so on. Okay, after repeating this training process, and typically we use number of measurements less than the number of antennas for the base station and the user equipment. Okay, so the received signal at the end of the training stage, uh, we can stack these measurements and we will get this form. Now we will try like to use this vectorization for y. We will apply it for this term, second term. Okay, now we will use the first trick. Again, we know HBU is the multiplication of these matrices, which represent like the steering vector like combined in a matrix form, and this beam space representation for the channel, and again applies the same trick. We will end up with this form. However, like we want to estimate this pi and var phi and the alpha, the complex gain, we assume that these like angle of arrival vectors and angle of departure are taken from a grid. Typically, we use the size of the grid is larger than or equal for the antenna size. Hence, we can like say approximately by neglecting for a large grid. We can neglect the grid quantization error, and we will end up that the received vector after the training process is the multiplication of these three components. The first one is called the measurement matrix. The second one is the dictionary matrix. And here, sigma bu is the sparse vector that we want to estimate. Okay, and we typically in compressed sensing, we say this measurement matrix multiplied by this dictionary matrix is called the sensing matrix. Okay, now we end up with the formulation for compressed sensing for user equipment communicating with base station, and now we will add the RIS. Okay, and before going to add the RIS, let me say that after this formulation, we can simply apply, for example, like very like well-known algorithm, which is the OMP, orthogonal matching pursuit, to estimate the channel parameters. Okay, let us move and add the RIS. Okay, what will we have? Now the channel is a little bit more complicated. H we will denote it with for the conventional model without any mutual coupling. HCV is the multiplication of the channel between the user and the RIS, multiplied by the RIS response, multiplied by the channel between the uh, active RIS and the base station. Okay. However, by using the same analysis, we can get the training. Okay, but here we have some different step. Here we will add also like in addition to the random precoding and combining vectors for the user equipment and the base station, we will add training for the RIS. And what we mean by any RIS configuration, we mean by that we are changing both the amplitude and the phase shift for the elements of the RIS. Okay, so here we assume we are like considering MI RIS setup and MB random training vector for the user equipment and the base station. Okay, let us first consider one training beam, which is like we have a setup for this RIS and a setup for the user equipment and the base station. The received signal, of course, with proper definition of the noise, we can write it as FBMC multiplied by HCV. Here the notation for MI, because we can see that this RIS configuration is changing with each setup, multiplied by the combining weight vector, the Hermitian of this vector. Again, we apply like the first trick, we get this formulation. Now let us consider this part. Okay, once we want to vectorize this cascaded channel, we will use the beam space representation of each uh, part of the cascaded channel. We apply this trick like again and again till we end up with this part. Okay, we can see that we have somehow a dictionary related to the user equipment and the base station, and it is a chronicle product between these matrices, a vector we want to estimate multiplied by this part. Okay, we can see this is a chronicle product multiplied by vector for a matrix that is diagonal. Okay, then we use the second trick we talked about before. Then we can convert this chronicle product to column-wise row product. Okay, good. So now we can like continue like our like applying the tricks because this is related to the RIS configuration. It will be multiplied again using the first trick chronicle product with this measurement. This measurement is related to the RIS. However, okay, let me, before like continue this formulation, see what is the effect of changing this model to a mutual coupling aware. So, but as a conclusion, we can see that the most important trick we used here depends on the diagonal structure for the RIS response, as we can see from here. Okay, let us change the consideration for the channel model and use the accurate model, which is account for the mutual coupling. Then, using the same logic, we are interested in vectorization of the cascaded channel considering the mutual coupling. We will end up with this terms. Okay. Unfortunately, as we can see from here, this is a full matrix. Okay. It's a non-diagonal matrix. So we cannot use the same trick as before and convert this chronicle product to a Hartree row. And actually, this is the effect of the mutual coupling. Okay, what we can do to get the like final formulation, we continue our derivation by collecting like MI by MB measurement. Okay, so as a conclusion, after we do all of the concatenation, we end up for a unified model for the conventional and exact. By exact here, I mean like the mutual coupling aware model. The received signal is a multiplication by a matrix called the sensing matrix multiplied by a vector, unknown vector, plus noise. Okay. The noise term is considering, of course, training and two terms of noise. The first one is related to the base station, the additive white Gaussian noise on the base station side, and the second one is related to the active RIS multiplied by the channel between the RIS and the base station. And sigma bar here is a sparse vector we want to estimate, and the sensing matrix, as we previously see, it's a multiplication of two matrices. The first one is a measurement matrix, and the second one is the dictionary. Okay, let us focus first on the measurement matrix. As I explained before, like we have a gamma, we have two parts for the measurement. The first part is related to the training vector here from the user equipment and the base station, and the second part is related to the RIS. And this part will differ between the conventional model and the mutual coupling aware model. The second matrix is the dictionary matrix, and again, it's multiplication, or sorry, it's a chronicle product between two matrices. The first one we previously see, it's a chronicle product also between the dictionary for the user equipment and the dictionary related to the base station. And this matrix, AUB, is a chronicle product with another matrix that's changed between the conventional model and the mutual coupling aware model. Okay, let us take a look further about these two matrices. As we can see, we have, okay, we have the sensing matrix. It has a common part and a part that is different because of the mutual coupling, and the same thing applies for the dictionary. Okay, so in the conventional model, this theta CV is equal to the phase shift for the training and of course the amplitudes, and it is a matrix with dimension Ni multiplied by Mi. However, for the mutual coupling aware model, this training measurement matrix related to the RIS containing these vectors, and each of these vectors, due to the mutual coupling, is with dimension Ni square. Okay, so the total matrix size is Ni square multiplied by M1, which is much larger size. Here it's related to Ni, the number of rows, but here it's related to Ni squared. Okay, the second matrix, which is related to the dictionary. Here, for the conventional model, we can see that it's a Kronecker product with a II, we denote it with CV, and it is, fortunately, it is related to the Khatr row product of the dictionary related to the RIS. We can see that the size is Ni multiplied by grid size square. However, fortunately, it has been shown in reference to proposition 1 that the number of columns for this dictionary is uh, is not GI square. Actually, there are significant redundancy in this dictionary, and we can end up with a dictionary that is related to GI, not GI square. So, as a conclusion, the total dictionary used for this cascaded channel for the conventional model is related, the number of rows is related to the multiplication of the size of the user equipment, number of antennas, the base station, and the RIS. And the number of columns is somehow related to, or let's say, it's from the order of GI, GU, GB. However, for the dictionary in the mutual coupling aware, unfortunately, such a diagonal structure we don't have, and we end up with a dictionary related to the RIS is a Kronecker product, which is, as we can see here, it's related to it's a quadratic function in both the number of rows and the number of columns with Ni and Gi. Okay, so unfortunately, this Kronecker-based dictionary does not pose any redundancy as we see that we have seen for the conventional model. Okay, so let us now get the conclusion for the first question. Can we formulate the channel estimation as a compressed sensing? Yes, the answer is yes. We presented a new compressed sensing formulation that accounts for mutual coupling without any loss of accuracy. Okay, so we mentioned that we can apply like OMP directly to solve the problem. Let us see what will happen if we do so. For the mutual coupling and aware model, which is a conventional model, we are comparing the complexity with applying the OMP for the mutual coupling aware model. We have two parts because there are large matrices need to be saved, the dictionary matrix and so on, and those are offline operation, and we have online operation related to the greedy search in the OMP. As we can see here from the analysis, for the online part, the complexity is O for G bar CV, which is, as we mentioned before, is related to GB, GU, and GI. However, for the same operations, once we consider the mutual coupling aware model, it's related to G bar MC, which is related to GI square, not GI here. Also, for the offline operation, here we have the same parameters, and here it's related to Ni, the RIS size, and multiplied by G bar CV. Again, it's related to GI. However, for the mutual coupling aware model, the complexity is related to Ni square and GI square. Unfortunately, for large RIS, this is an affordable complexity. Okay, so now we get the answer for our second question. What is the advantages or disadvantages for this compressed sensing model? Unfortunately, due to the existence of matrix S, the RIS response is no longer diagonal, And the compressed sensing, as we have seen, incurs a dimension increase in the basis space. Okay, so here we ask ourselves as third question or fourth question, can we do better than just applying OMP? The answer, like we will see in the next slide, we are trying to understand more about our problem and the effect of the mutual coupling and see if we can get a accurate solution, but with much lower complexity. Okay, let us move to see how we will propose like low complexity solution to estimate this cascaded channel. Okay, so let me first explain what is the intuition behind our proposed algorithm. Actually, to understand why we will do so, let us just like take a brief discussion about OMP. Typically in OMP, this is an iterative algorithm. For each iteration, we take the received signal, we do a correlation with the dictionary, with the sensing matrix. Okay, so we can understand this as a greedy algorithm that search over the whole number of columns of the sparsifying dictionary. Then, like, we thought about, okay, if we have somehow any meaningful initial estimate or prior information, for example, we know like the angle of arrival, angle of departure must lie in this region, for example, okay? And okay, if we reduced instead of like searching over a very large sparsifying dictionary, can we like build a reduced space dictionary, for example, over only this number of columns, which is like a region around this angle? Okay, and once we build this reduced space dictionary, okay, uh, we can then have a low complexity solution. But here we have two questions. The first one, we need a meaningful initial estimation. So our first idea was, okay, can we use the conventional model as a coarse estimation? Actually, the answer is yes. And why this makes sense? Okay, so if we look deeper into the vectorization of the cascaded channel with the mutual coupling, we can notice that the last term, which is the effective risk response, can be written by using the Newman series expansion as these terms. Okay, and if we take the first two terms, then after like some like mathematical like steps, we can get approximately vectorization for the conventional model plus additional terms for what we want to estimate multiplied by this term. Okay, let us look a little bit about these terms. The first one is the two terms that we took. The first one is the conventional risk response. This is what, and here we will get the cascaded channel for the conventional model. The second term is basically we have the scattering matrix on the diagonal. We have the reflection coefficient, and the non-diagonal elements are representing the mutual coupling. But typically, this value like will be minus 10 dB, for example, or so on. And here we have like the amplitude, somehow the amplitude squared for the active risk. So we can see uh, this is like a very good estimate in most cases. This is why we think this conventional model is making sense as a coarse estimation. Okay, let's move to the second step, which is like how to design a dictionary that is a reduced space over the complete dictionary and also have a sense like related to this initial estimate. So our second idea is let us take the initial support and build a sub-dictionary. And this dictionary, we will build a region around this dictionary, and then we will use it for the estimation. Okay, so we propose a dictionary reduction algorithm that takes three inputs. The first one is a subdictionary that is built upon the indices of the previously estimated support. We call it the initial support. Second input is uh, the dictionary over the whole region. Okay. Then this G is different from the previously one mentioned. This is the number of the columns for the reduced dictionary uh, the reduced dictionary one that we will use later. Okay, this number typically we can control it and we can choose it like much lower than, for example, like the number of the elements of the RIS. We can use it, for example, ni over 2 over 4, whatever. Uh, this is a parameter that we can control. Okay, and then what the dictionary reduction algorithm performs, it takes those two dictionary, it do a correlation, and it only select the largest correlated columns. And this is the output. We can think about the output. For example, let's assume in the initial support, we have only one direction, which here in red, and we want a dictionary with size of 7. So we will end up using this algorithm with a dictionary, ADR, which consists of these 7 beams or 7 columns of the dictionary that are centered around this initial support. Great. Now we have all the components for our proposed algorithm. Let us like move into the whole algorithm. We call it like two-stage mutual coupling aware channel estimation. The input is the received signal, which is like following the exact model. Uh, we first start by a coarse estimation. We are estimating the mutual coupling aware received signal model, the exact model, by using uh, the conventional model. Okay, using the OMP. This is just to get a coarse estimation. The second stage, we get a refined estimation where we use the support of the estimation to build this dictionary. And we use this dictionary, we apply the dictionary reduction algorithm to get a new dictionary, AIDR. Then we do a chronicle product with the product related to the user equipment and the base station. And now we see that this dictionary is have a size much lower than the original large dictionary, which is the chronicle based one. And then we compute a new sensing matrix we called uh, with the subscript dr, and then we using this sensing matrix we do a second OMP, and then we have two things. The first one is the sparse vector we need to estimate, and using the support for the from the OMP, we can estimate the angle of arrival and the angle of departure vectors. Okay, so here we end up with an algorithm which is low complexity to estimate the channel. Now we will move to the second stage, which is the beamforming, and this part will be presented by my colleague Punjan.
Okay, now we consider how to configure the system based on the estimated channel, which is also called the beamforming problem. Generally, we can leverage the channel reciprocity to do this. We first do channel estimation in the uplink stage, as presented in the previous slides. So we have the uplink channel. Then we can infer the downlink channel using channel reciprocity. As you can see, the uplink channel and downlink channel, they are quite symmetric. So that means once we know one of them, we can know the other one immediately. Then we will do the downlink beamforming based on this inferred downlink channel. But if you remember what Simon has presented, the proposed channel estimator doesn't obtain this uplink channel directly. What it provides is an equivalent channel denoted as GUL, as here. And we can also infer its downlink counterpart as GDL by rearranging those elements. So our beamforming will be based on this GDL matrix. Again, this equation summarizes the second model we use and what we can configure are the precorder at the base station and the combiner at the user equipment and the RIS response. Here, omega denotes the total noise that we have at the receiver, which can be expressed in this form. So if we consider active RIS, the noise at the receiver is a combination of the thermal noise at both the RIS and receiver. This omega u is the noise at the receiver, and this omega I is the noise at the RIS. Um, but based on our simulation, the noise term generated at RIS can actually be ignored in the far-field scenario. Here we have a figure to show this. As you can see, this part of noise is typically orders of magnitude lower compared to this term. So that means uh, this can be reasonably ignored. Then we can simplify the SNR in its form, and so what we need to design or optimize are these three vectors. Consequently, we can formulate such an optimization problem to describe this joint beamforming problem. The main problem here is that we don't have these channel matrices HUI and HIB exactly. Again, what we have is an equivalent channel GDL as we have mentioned. And this equation means that if we fix the RIS response gamma, we can have a cascaded channel HUIB immediately. So we can solve this joint optimization problem using alternating optimization steps. So, and here we consider analog beamforming architecture as an example. So in first step, we can fix precorder W and RIS response gamma and optimize combiner F only, which has a closed form solution as shown here. Then in the second step, we update and fix combiner F and RIS response gamma and optimize precorder W only, which also has a closed form solution. The main challenge lies in the third step where we optimize the RIS response gamma given updated precorder and combiner vectors. We can first define vector T as this. Note that GDL is the channel information that we have. Then the original optimization problem can be recast in this form, but this is non-convex and more importantly is intractable due to this matrix inversion here. So to make it more trackable, we can make a approximation using Newman series expansion as shown here. So if we only preserve the first two terms and substitute them into this objective function, it becomes like this. This is more trackable as there is no matrix inverse operations and more. Although this is still a non-convex problem, we can use some non-convex optimization techniques to solve it. And in this paper, we present a solution using successive convex approximation.
Okay, to present the simulation result, but before doing so, I want to mention that the MATLAB codes are linked with the paper on IEEE Explore using CodeOcean, and also they are available on GitHub. So you can use these codes and reproduce the results that we get in this paper, and don't hesitate to reach out to me or to Punjan by email if you have any question. Okay, so for the considered like setup in the this simulation, it's explained in the paper. We are presenting some results. The first one, we are like plotting the estimation NMSE in dB versus the UE transmit power. Okay, here we are plotting mutual coupling and our model. Uh, so mutual coupling and our OMP and the proposed algorithm. In black, we can see no diction reduction, which means like we are applying the mutual coupling aware OMP, the most complex solution, and our two-stage with different row. What is rho dr here? Here, rho dr is the ratio of the number of columns that we used in the proposed diction reduction algorithm and over the number of columns for the uh, dictionary for there is a chronicle product one, which is like related to GI square, and GDR is like somehow an I by half or 1/8. So we can see this is like a small ratio from the overall dictionary. So we plot for different value of rho. So here we have two important observations. First of all, taking into account the mutual coupling result always in a better estimation than like neglecting the mutual coupling aware and apply a mutual coupling unaware algorithm to the case where there exists a mutual coupling. The second observation that our proposed solution, even with very low number of selected column, we can see it reached like very similar to the exact solution, which is the highest complex one. Okay, and this is like the first result. The second one, we are evaluating again the estimation NMSE versus like there is inter-element spacing. Why we are doing so? Because we know once we have very large separations, the mutual coupling effect is very negligible. For example, like typical case, we know like for lambda/2, this is negligible. And when we have very small inter-element spacing, for example, these values, the mutual coupling is very large. Okay, what we can observe here, two important things, like for like large spacing where the mutual coupling is like negligible, we can see all the methods have the similar performance. However, once the uh, mutual coupling effect is very large, the mutual coupling unaware totally fails in this case, and the degradation, as we can see, is very large. Okay.
In this figure, we evaluate the communication spectral efficiency as a function of transmit power. We compare our proposed method with a few benchmarks. We can observe that the proposed method consistently outperforms the adopted benchmarks. And we also tested it on both the ground truth channel information and the estimated channel information using our channel estimator. It turns out that the proposed beamforming algorithm works well with the estimated channel. Then we test the spectral efficiency as a function of the inter-element spacing of RIS. Basically, a shorter spacing will result in a stronger mutual coupling. And we see as the impact of mutual coupling increases, the performance gain of the proposed SCA-based solution initially improved, but eventually declines. This is because when the mutual coupling is too strong, the use the Newman series approximation here becomes inaccurate. But the proposed method is consistently better compared to benchmarks. Thank you so much for your attention. If you are interested in this work, welcome to read this full paper to find more details.